Welcome to the lecture on control engineering. So I will be taking you onto the applications of the complementary filter. So the complementary filter is a sensor fusion algorithm where we calculate the angle from the accelerometer, and then after the angle computation block from the accelerometer we get the angle underscore accelerometer. We pass it through the low pass filter and bring it into the combination block. From the gyroscope we also get the angle by numeric integration. The formula for numeric integration is shown below. This angle from the gyroscope is passed through the high pass filter and it comes to the combination of the low pass filter of your angle from your accelerometer and your high pass filtered angle from your gyroscope. So as discussed previously, the complementary filters equation is as follows: theta Cf is equal to alpha, which is your filter coefficient of your complementary filter, into the theta of the high pass filter, which is the angle which comes from the gyroscope, plus 1 minus alpha Cf into the theta which comes from the angle calculated from the accelerometer. So these two are combined depending on the dynamics of the movement that we have. The complementary filter equation is this, where theta Cf is your filter coefficient for the complementary filter, theta Cf is the angle computed from the complementary filter, the theta high pass is the high pass value of angle from your gyroscope, and theta low pass is the low pass value of the angle from your accelerometer. So I will be showing you the MATLAB implementations of why we use the low pass filter and the high pass filter, and how do we combine these two angles from the accelerometer and the gyroscope in the complementary filter. Here are the three codes that we have for the actual implementation of the high pass filter for the gyroscope angle, and the low pass filter from your accelerometer angle, and the complementary filter block which combines the high pass filter and the low pass filter angles in one particular computational block. So I will show you first how we have the drift in a particular stationary position and how we correct the drift in this particular experiment. So here we have a CSV file which is in the name stationary.csv. I will show you the Excel file for that. So this is the Excel file where we have collected data from an IMU that we have. So this IMU consists of an accelerometer and a gyroscope, where the accelerometer is the ADXL 345 and the gyroscope which is LG 34200D. So here we can see that how we save the data is column number A, which is axle X. So this is the axis of the accelerometer which is pointing forward. So if we consider this to be the accelerometer and I keep it stationary, the axis which is pointing forward is the X axis. The axis which is perpendicular in this manner is the Y axis, and the axis which goes through the device is the Z axis. So axis X of the accelerometer is in column A, axis Y of the accelerometer is in column B, axis Z of the accelerometer is in column C. The same holds true for the gyroscope when kept stationary. So the axis X of the gyroscope is in column D, the axis Y of gyroscope is in column E, and the axis Z of the gyroscope is in column F. So I go back to the MATLAB code and I read these values into a particular variable. So from the file I get into a variable which is called data. So my axle X is the first column, as we know, so we call it from the first column. Axis Y is from the second column, accelerometer Z is the third column, so we call it respectively. The gyroscope data which is the X axis gyroscope data is in column number 4. The gyroscope Y data is in column number 5, and the gyroscope Z data is in column number 6. So this is how we read the data from the CSV file. After reading the data from the CSV file, we calculate the mean bias value. As Professor Vishwanath has already spoken to you about bias, we will be calculating the bias of these values that we have in an experiment where we have collected the data. So we take around 200 samples. We calculate the sum of these 200 samples and divide it by 200. So we get the mean bias, which is in a stationary condition, of the x, y and z axis of the gyroscope. This mean gyroscope value has to be subtracted from each of the axes. Now we consider only the y axis, so I am subtracting the gyroscope mean value of y into the gyroscope y value. So the bias is basically removed. So here are some experimental results of the bias, where x axis is measured as 0.04, the y axis bias is measured as 2.85 and the z axis bias is measured as 1.029. So here this is an experimental setup where we have measured these bias, which may not be true all the time. So if you want to calculate the bias, we have to keep the IMU stationary on the ground and calculate the bias and remove the bias initially from the gyroscope value. Okay, so next we would say what is the data rate at which we are getting the data from the accelerometer, the gyroscope. So the data rate at which we are getting is around 200 samples per second. It's in the code where we actually call the data in at this sample rate. So we get 200 samples per second. So Ts, which is also delta T, is 1 by 200. So this is the delta T where we need to compute the alpha for the high pass filter and the low pass filters. So here specifically for the high pass filter. So as we know that the sensor is kept stable on stationary on the ground on the table, so we consider the first value of the angle of the y axis to be 0, and we have a for loop where we integrate the gyroscope y value. As we said, we consider the y axis, you can consider the z axis or the x axis, but here in this case we are considering the y axis. So we keep the y axis stationary or the IMU completely stationary, and we calculate the angle from the y axis. So ang y is a variable where we get the value of the angle from the gyroscope. So if I plot this value of the gyroscope, so here is the graph of the angle measured by the gyroscope. So the y axis is measuring the angle, the x axis is measuring the samples. So we can see that over a period of time, which is around 8000 samples, my value of drift, my value of the angle, which is when kept stationary, has moved from 0 to around 2.25. So we see that there is a lot of drift in this experiment that we have conducted. So how do we remove the drift of the angle computed from the gyroscope? Is by passing through the high pass filter. So I will be telling you how to pass it through the high pass filter. Okay. As we have seen how to calculate the filter coefficients previously in the lectures given by Professor Vishwanath, I will be going through the same again. So Fc is the cutoff frequency, where Fc is equal to 1 by 2 pi Rc. Now we calculate for Rc, which is your time constant tau, is equal to 1 by 2 pi Fc. From this we calculate your tau value as tau is equal to Rc, and when you want to calculate the filter coefficient, alpha Hp is equal to tau divided by tau plus delta T, or in this case it is mentioned as Ts. So the filter coefficient that we have calculated is for 3 Hertz. Your cutoff frequency of this filter is at 3 Hertz. and we get the alpha value of 0.8641. So we pass the angle computed from your gyroscope through the high pass filter using this filter coefficient. So now that we know that the alpha which for the high pass filter is 0.8641, we put it in the high pass equation which is defined previously, which is explained to you by Professor Vishwanath. So we get the value of the high pass signal as ang gyro yHp. So if I have to plot this value of ang gyro hp, I would get a graph which looks similar to this. Yeah. Now you can see that your blue line as seen previously is your angle from your gyroscope, which is drifting off even when kept stationary, and when we pass it through the high pass filter, we get a very smooth line which is almost at 0 all the time. So here is how we correct the drift from the angle of the gyroscope by passing it through the high pass filter. Now I will be taking you through how to reduce or how to reduce the jitter from your accelerometer by passing it through the low pass filter. Yeah, so all these codes are available in your forum. If you have any doubts with the codes, you can always contact me. So over here we are getting the data of the same stationary value. We know that your accelerometer data is in column number 1, accelerometer y is in column number 2, accelerometer z is in column number 3. Here we do not consider your gyroscope, but for computational sakes I have given the values over here. As we note from the previous experiment for the high pass filter, Ts is your delta t and my sampling rate is around 200 hertz. So I get 200 samples per second, where delta t is 1 by 200. This has to be checked properly while you are conducting the experiment, because every time you will not get a standard data rate unless you have defined your data rates well. So please check this before you use the same code. Now we calculate the angle from your accelerometer. So the angle from your accelerometer is calculated using this formula. So we have already shown to you as what the formula for the accelerometer angle computation is. So this is how we implement it in MATLAB. So once we have got this data, I want to design a low pass filter for this accelerometer data. So as shown before, I will go through the cutoff frequencies and how we calculate your filter coefficients from the cutoff frequencies. So Fc is your cutoff frequency, where the formula of Fc is equal to 1 by 2 pi Rc. Rc is also your tau, which is your time constant, which can be said as 1 by 2 pi Fc. So now your alpha for a low pass filter is delta t divided by delta t plus tau. Once we substitute the values of tau and delta t or Ts in the equation, we get the value of alpha for the low pass filter. Again over here, the alpha for a cutoff of 3 hertz is around 0.0909. So we consider this 3 hertz as for the high pass filter. We have also considered the 3 hertz as the cutoff frequency. We consider the 3 hertz cutoff frequency even for your low pass filter. So we pass the angle computed previously from your accelerometer data through the low pass filter. So this is your equation which is being implemented in MATLAB. The equation is previously shown. So you can implement this equation for your low pass filter in this manner. Once we pass the accelerometer data through the low pass filter, we can see how we remove the jitter from the angle computed from your accelerometer data. So here is the graph where when kept stationary, the accelerometer is not moving. So we need to get an angle which is ideally a straight line, but as we see that the angle calculated from your raw acceleration value, which is in terms of rad, has a lot of jitter, and the angle computed after passing through the high pass, the angle computed from your accelerometer after passing through the low pass filter is in yellow. So, we can see there is a considerable amount of jitter which is being removed while passed through the low pass filter. So, now I will be showing you on how we combine the low pass filter and the high pass filter to get the complementary filter. Now I will be showing you how the complementary filter block is designed, where we combine the angle calculated from the gyroscope and the angle calculated from the accelerometer in the previous experiments as shown. Over here the basic steps are very similar. So, we have the data we read from the stationary file, and then we assign it to variables which are ACC x, accelerometer x first column, accelerometer y the second column, accelerometer z which is the third column, the fourth is the gyroscope x, fifth is the gyroscope y, and sixth is the gyroscope z. So, we find the mean which is the bias, and we remove the bias in this way, and we know that the Ts, which is the delta T, is 1 by 200. So, now we need to calculate the angles from each of the data, each of the sensor, which is the accelerometer and the gyroscope. So, we find out, we keep the initial condition from the accelerometer, which is this formula a tan 2 axle x divided by square root of y square plus z square, and the gyroscope is also initially given the same angle, which is axle x divided by root of tan inverse of axle x divided by square root of y square plus z square. So, now here we calculate the angle from the gyroscope in this way, and we calculate the angle from the accelerometer in this way. Now, we have the complementary filter, which is a combination of your low pass filter with the high pass with your high pass filter using a particular filter coefficients. Here we know that we have a stationary position, so we need to trust the accelerometer more than the gyroscope, because the gyroscope has drift. So, we choose our filter coefficients of our complementary filter in this manner, where we choose 1 minus alpha is equal to 9.98 and alpha is equal to 0.02. So, now we can plot this signal. So, we get it in this manner as we have seen previously. The blue line is the angle computed from your gyroscope, and the green line, which is superimposed by the red line over here, is your angle computed from your accelerometer, and the red line is the actual complementary filter angle. Now, this is done without filtering, without passing each of the angles through the high pass filter or the low pass filter. So, let us see on how the dynamics change when we pass the angles calculated from the gyroscope and the accelerometer through the high pass and the low pass filters. As previously calculated, our filter coefficients for the low pass filter and the high pass filter is as follows. The alpha for the high pass filter is previously calculated as 0.8641, and for the low pass is 0.0909. We have seen that in the previous experiment as to how we calculate the alpha values. We initialize the values which are required for the computation of these angles. Now, we compute the angles of the accelerometer using this formula. After computing the angle, we pass this angle which is axle 1 into your low pass filter, where your accelerometer data of the x, y and the z is passed through the low pass filter. Next we compute the gyroscope angle in this way. So the ang gyro is added with the gyroscope y value and multiplied with delta t, where the numerical integration is the gyroscope into delta t, which gives you angular position. So now we pass this gyroscope value through the high pass filter. The high pass filter of the gyroscope, the angle calculated from the gyroscope is this equation. So the equation is already previously mentioned, where we pass the angle from the gyroscope through the high pass filter. Now we see that this two have to be combined using the complementary filter. So the filter coefficients from your complementary filter is alpha is equal to 0.02 and the 1 minus alpha CF is equal to 0.98. So now we can see the difference in the graphs that we get with pre-filtering and without pre-filtering from the high pass and the low pass filters. Yeah. On the left side we see a plot which is the angle calculated from your gyro, which is the blue graph. The angle calculated from your accelerometer is superimposed by your complementary filter, which is the red graph, but the green graph is your angle computed from your accelerometer. The red graph over here is the complementary filter angle. So here we do not pass the angle from your gyroscope or the angle from your accelerometer through the high pass or the low pass filters respectively. We just pass it, we just combine these two angles directly to get the complementary filter. On the right side we have the angle from your accelerometer, which is in green, the angle from your gyroscope, which is in blue, and the angle from your complementary filter, which is in red again. Here we pass the angle computed from your gyroscope and your accelerometer through the high pass and the low pass filter, and we combine these two to get this complementary filter value. I will tell you why the gyroscope value is towards 0. That is because we see over here that the gyroscope is basically stationary. So now the movement or the angular velocity which is present in the gyroscope is very low. So we pass it, when we compute the angle, it is basically a stationary angle with lower frequency dynamics. As we see that the angles computed from the gyroscope, when passed through the high pass filter, the lower frequency which is below the cutoff frequency is actually filtered out and attenuated. Hence we get the value which is close to 0, because all the frequencies which are present in stationary is actually attenuated by the high pass filter and we get a 0 angle. So now we can see that in a stationary condition where the sensor is not moving, we can trust the accelerometer more than the gyroscope. So now we have seen the complementary filter where we combine the angles computed from the accelerometer and the gyroscope, which is passed through the low pass filter and the high pass filter respectively in a stationary position. Now I will show you an experiment where we have actually taken the gyroscope which is strapped onto the hand, and we move the gyroscope and the accelerometer, which is the sensor which is over here, in 0 to 90 degrees manner and bring it back to 0 degrees. So it goes from 0 degrees to 90 degrees and back all the way to 0 degrees. So here is a file where which is called movement.serial. I won't run through the code because it is the same code. I will just show you the graphs. So the graph on the left, which is your figure 1, is where we find the angle from your accelerometer and the angle from your gyroscope without passing through the high pass and the low pass filter, and combining these two angles together in a complementary filter. So here we can see that the blue line is the angle computed from your gyroscope. The green line again, which is superimposed by the red line, is your accelerometer angle, and we see that the red line is your complementary filter angle. Here we can see the value of drift, where we can see that the angle computed from your gyroscope is drifting in a way where we get peaks from 0 to around 60 degrees, but at sample number 7000 we actually start the angle value from 60 degrees to around 120 degrees. So here we can see the gradient in which there is the drift. So now again on the right side we have the angle computed from your gyroscope, which is the blue line, the angle computed from your axle, which is your green line, and the angle computed from your complementary filter, which is the red line. Here we can see that, so once we compute the angles and pass it through the high pass and the low pass filter respectively, we get this kind of a response from the complementary filter, which is your red axis. After computing the angles, we see that we are trusting the accelerometer more than the gyroscope, but we can play around with the alpha value of the complementary filter to trust either the accelerometer or the gyroscope. We would trust the gyroscope more in a fast dynamic movement. So an example to show you how we can trust the gyroscope more, on the left side we can see that till sample number 3000 we have a slow speed motion where we do not move very rapidly. We have a value where we compute in a very slow manner. On the right half, where we start from around 6500 to 8000, we have fast dynamics. So here if I zoom in to the plot, you can see that the frequencies above 3 Hz also are captured from what is compared previously. There are the dynamics of the fast motions which are also captured. So here we can actually compute the complementary filter by trusting the gyroscope more. So now that we see that the higher dynamics of the gyroscope, where the gyroscope can be trusted more, I request you to play around with the alpha of the complementary filter, where if you trust the gyroscope more, where the alpha CF is given a higher weightage towards the gyroscope, the complementary filter will actually follow the gyroscope. So I request you to please try by changing the alpha for the complementary filter. If you have any doubts, you can contact me on the forum. All these codes are posted over there. You can get in touch with me. Thank you. All the best.